All right, so let's shift gears from Chapter 7 to Chapter 8. Chapter 7 was flow over external surfaces. We looked at flat plates and we looked at cylinders, circular cylinders, square cylinders. Now we jump to Chapter 8. Now we look at flow inside of tubes and pipes and cylinders. So internal flows, Chapter 8. So here's how we start the model. We say, now this picture up here, this is a circular tube, diameter. This is the tube. Diameter is D. We measure X along the tube axis. Anytime we've got convection heat transfer, we pretty much have to go first to the fluid situation. We have to understand what's going on in fluid mechanics before we tackle the heat transfer. So here's the fluids picture, and this might be a review for you from your fluids class. First of all, nomenclature. U sub M. Now, let's go back. Chapter 7, flow over external surfaces. The free stream velocity was capital U subscript infinity. Flow over a circular cylinder or a square cylinder. Capital V. Those were the velocities. Now we're in Chapter 8. What's going to be the velocity now? Well, little u. We shift gears just little u. The M stands for mean, the mean velocity. So here's the velocity coming into the tube. It's uniform. It comes into the circular tube. A boundary layer builds up around the perimeter of the circular tube. This velocity boundary layer grows thicker and thicker until eventually it meets at the center line of the tube. Where it meets at the center line of the tube, the boundary layers meet. That distance is called X subscript FD. FD stands for fully developed. Beyond that point, now if this is laminar flow, at that point we would have a parabolic velocity profile. If we go down a distance down here, we still have the same velocity profile. Okay. So this region where the velocity profiles don't change is called the fully developed region. The region where the boundary layers develop and meet at the center line, this distance is called the X location where it's fully developed. So X subscript FD, fully developed distance. Now, we shift gears to heat transfer. Okay, now look at temperatures. Here's our situation here. We're going to assume in this picture that the tube surface is held at a constant temperature. T sub S, S stands for surface. So the tube surface is held at a constant value. The fluid comes in, T subscript MI, the I stands for inlet. So this is the inlet mean temperature. It's uniform. It comes in, just like flow over a flat plate. A boundary layer develops around the perimeter of the circular tube. Eventually, the boundary layers meet at the center line. That distance is called X subscript FDT. The T stands for temperature. Fully developed temperature distance. Beyond that point, we call it the fully developed region, but the temperature profiles do change shape. Here it is just after they meet. Here's the temperature profile. Go down a little ways on the tube. Notice it's getting flatter in the middle. Go down further. Eventually, it becomes totally flat. Totally flat. An example. Let's say the tube surface is held at 100 degrees C, and the fluid comes in at 30 degrees C. You know eventually all that fluid is going to be at 100 degrees C if you go down far enough. If you go down far enough, these profiles, temperature profile, it'll become uniform at TS. The fluid is heated and heated and heated until its temperature totally across the cross-section is TS. Okay, so there's what happens inside the tube as it's developing flow. Now, there are two conditions that can occur in a tube. And we'll mention these in a little more detail in a few minutes, but for right now, we can have a constant wall heat flux on the tube. Constant wall heat flux on the tube. This picture down here is for a constant temperature. TS doesn't change. Okay. This one up here, this stands for surface. Heat flux on the surface. Okay. So now we're putting the same heat flux in the tube as we go down in the x direction. So we're going to try and find how the temperature varies. So we do an energy balance on a differential element. So here's my little differential fluid element. It's a distance dx. Comes in, T mean, goes out, it gets hotter, T mean plus dt mean. All around the perimeter, I'll just show it here, but all around the perimeter, we have a constant surface heat flux. All around the perimeter. The fluid's going to get hotter, okay. We run a little energy balance on this differential fluid element. First of all, how much heat comes into the fluid? Well, here it is. Qs double prime times dA. Watts per square meter times square meters is watts. What area does the heat flux act on? The perimeter times dx. That's the area through which the heat flux goes. P dx. P is perimeter. What does that do? It raises the temperature of the fluid. Here it is, thermo, m dot C sub P dTm. That's how much the temperature changed. So energy coming in from the heat source equals the energy added to the fluid to raising its temperature. We then separate variables. dTm divided by dx equal Qs double prime perimeter divided by m dot C sub P. Got it. The right-hand side is a constant. Qs double prime a constant, perimeter a constant, m dot a constant, C sub P a constant. Integrate this guy. dt, or Tm as a function of x equal the temperature coming in, that's the constant of integration, plus this constant times the distance x. Notice it's linear with x. So the temperature increases linearly with x. Now, we look at another case, the second case, for constant surface temperature. You can go through the same little exercise. Take a differential element, write an energy balance on it. We're not going through it, but you write the energy balance, okay, and you set it up just like over here, except now the temperature of the surface remains constant. And we end up, let's see here it is. Ts minus Tm as a function of x divided by Ts minus Tmi exponential Px m dot Cp h. So, this is, of course, exponential. So now we have two cases there of how the temperature varies, the mean temperature varies with X if it's constant wall heat flux, if it's constant surface temperature. Let's define what that mean temperature is, though. Tm. Mean fluid temperature. Okay, so to do that, we're going to go back to chapter 1. E dot. E dot is energy, joules. Dot means per time, joules per second, watts. So that E dot stands for, if I put my hand here, that stands for the energy crossing my hand. How much energy goes across my hand at that X location? Okay. So let's write the expression then for that. So E dot M dot C sub P T mean integral across the cross-section area That's how we define the mean temperature. Don't forget thermal. The energy transport across that cross-section is m dot, C sub P, T. What's that temperature? The mean temperature. How do we get it? We integrate across the cross-sectional area of what? Rho, U, Cp, T, dA. What's the cross-sectional area? It's circular. What's the outside radius? R naught. Now, what's the differential element? In a circular geometry like this, we define the differential area as this, a very thin strip like this. That's dA. What's the radius to the center? R. What's the thickness of the strip? dr. What's the area? The circumference times dr. So dA, circumference, 2 pi r, dr. Circumference pi times d, 2 pi r, dr. That goes in here. So solve this guy for Tm. And that dA, let's leave We'll leave dA in there. Now we'll plug dA in there. So you could find that Tm at any location along that tube, but you need to know how the temperature varies with R and how the mean velocity varies with R. Plug it in there, integrate, and that would give you T mean. That's mathematically how we define the mean temperature. If you want a less mathematical definition of T mean, sometimes some people call that the mixing cup temperature. So if you would cut that tube at a certain location and let that fluid, say it's water, let that fluid go into a cup of water and then stir that cup of water and put a thermocouple in there, that's T mean. It's sometimes called the mixing cup temperature. So if you want to, not the mathematical definition, but in the world of the tube, you would cut the tube, let the water flow into a cup, stir the cup up, put a thermocouple in there, and that temperature you get would be the mean temperature. Okay. So, and why is the mean temperature important? Well, Q. Chapter 1, H, A, T, surface, minus T, M. Yeah. Chapter 7, what was in the parentheses? External flow. T surface minus T infinity. This is chapter 8. What's in the parentheses now? T surface minus the mean fluid temperature. So there's our Tm in the heat transfer equation. This is how Tm varies with X. This is how Tm varies with X. This is a mathematical definition of Tm. Newton's law of cooling. This now becomes T mean at any X location. Okay. One thing we didn't cover that we should have earlier is I meant to tell you how you get that X fully developed over there. So let's do that now. So let me go back. Okay, maybe what we'll do, we could do that, I guess. Yeah, let's go back and do that. I'm going to make some room here. I want to save. While I'm here, let me just go ahead and describe to you these two cases. Why are there two cases? Why is a constant wall heat flux and constant surface temperature? They're two frequently found situations in the real engineering world. So that's why our author presents these two cases. There's a lot of applications. I'll take maybe this one. I'll take this one first. When in the real world might you have a constant surface temperature? Okay. Constant tube surface temperature. Well, I'll give you one case. In your thermal class, you've got a condenser. Whose purpose in life is to condense steam into liquid water so the pumps can handle it and pump it back into the system. The steam comes in hot. In the tubes, water. Pacific Ocean, cool. Redondo Beach Power Plant. Pacific Ocean water inside, condenser. Hot steam hits the outside of the surface, condenses at what temperature? The saturation temperature of the pressure in the condenser. So the water droplets condense at the saturation temperature. They turn from steam to liquid water. They then run down the tube in the hot well here, where they're collected and pumped around. And of course, guess what this is? The temperature everywhere along here is the saturation temperature of the pressure in the condenser. Okay, that's him. That's what I'll use. Now let's take the case of, well, who's gonna put a constant surface or wall? This probably should be constant surface heat flux. Well, there's lots of cases there, lots of cases. I'll just give you one. Some solar collectors out in the desert use oil as a circulating fluid, not water, because water can freeze at low temperatures. So they use oil in the solar collector. And then the oil's collected and taken to a point where then it vaporizes the steam and creates steam and turbine and blah, 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 electricity. But the sun goes down at night and the oil's in the pipes out in the field. And the desert can get pretty cool at night. And then in the morning the sun comes up and the pumps go on. Ooh, they don't like high viscosity. They don't like that high, because that oil now is really viscous. It's been sitting all night out there in the desert and getting cooler. And that pump does not like pumping that viscous cold oil. So what they do sometimes is they'll wrap the pipes out in the field with electrical tape, like blankets, if you wish, and trickle electricity through it to keep the oil a little bit warmer so the pumps don't get that big boom when it turns on in the morning. That's constant wall heat flux. Every meter of that little blanket on those tubes generates so many watts to keep the oil warmer than it would have been in the desert in the middle of the night. So yeah, that's an application there. Maybe if you want to stretch it and just start with a very simplistic model, you can, besides what I just mentioned, you can take a parabolic trough collector carrying a fluid at the focal point there, fluid, and here's the tube, runs this way. Here's the parabolic trough collector. They're out in the Mojave Desert. We drive by sometimes going to Mammoth, Highway 395 and Highway 58. There's a big solar field out there. They've got parabolic trough collectors out there. And the troughs track the sun, sunrise to sunset. And here's the sun's rays coming in. Ooh, it almost looks like it's a uniform heat flux on the tube from the parabolic trough collector. Yeah, you could start out your analysis that way. It's not perfectly true, but not a bad starting point maybe. So yeah, there are many applications of both of these conditions. That's why we engineers are interested in both these guys. They'll appear a lot in our studies, designing heat exchangers, looking at solar collector fields, things like that. So yeah, big time situations. So that's why we study both these guys. Let's take a look. These are just little bits of odds and ends here right now. Let's look at another thing that I mentioned. How do I get the Reynolds number? Reynolds number D. rho UM D over mu. Chapter 7, what was it? Flat plate, U infinity, L over nu. Circular R square tubes. D, which stands for distance, okay? U infinity, D over nu. Now we go to chapter 8. What's the Reynolds number of chapter 8? Oh, flow inside tubes from your fluids class. Rho D over mu. In your fluids class, you probably call this V. That's okay. We call it UM in the heat transfer class. You've had thermo, and you know they in the second part of thermo they give you a big power plant, and there's a turbine, and there's a condenser, and there's a boiler, and there's blah blah blah, and they'll say, okay, find the temperature leaving whatever. I don't care. Find the output of the turbine. I guarantee you that nobody in that, no problem in that class with that. It could be a gas turbine, it could be a steam turbine. They didn't say, oh, by the way, the velocity in that tube is 10 meters per second. They never gave you the velocity in tubes. Nobody in the real world speaks like that. Ask the Edison people. Yeah. Ask the San Diego Gas and Electric people. They don't speak that language. They don't give you velocities in tubes. What do they give you? You know what they give you. The mass flow rate. Every problem in thermal with those guys, they always give you the mass flow rate. So we don't like that guy in tubes, chapter 8. We don't like him. I want to see mass flow rate in that equation. So go ahead, you can convert it, and you can end up with the mass flow rate in there. And let's see what we got here. Okay. 4m dot. 4m dot over, I think it was rho. Let me see, I got that. I better get that guy right. Oh, I know where it is. Here it is. No, I don't. Oh, there it is right here. 4m dot pi mu d, pi mu d. So this is what you want to use pretty much. You check out the homework. Every homework problem gives you the mass flow rate. Don't waste your time converting that to a velocity to put in the top equation. That's a waste of valuable time on a midterm. Use that equation to find out what the Reynolds number is. Okay, so let's take a look then at, let's see, I think I'll put that over here. Let's look at how the temperature varies. Let's take, let's see, constant surface temperature. Let's take him first, constant wall heat flux. Qs double prime equal constant. Okay. Okay, and let's look at him. T mean in, comes in, T mean in. How does the temperature vary with X? Linearly. Ts equal constant. constant surface temperature. Fluid comes in, mean inlet temperature. How does it vary? Exponentially. So there's our two temperature profiles that go along with those two boxed equations over there. The author also throws in, for interest's sake, how the surface temperature varies here. It comes up like this, then it is parallel to this guy here. This is T surface X. We don't have that equation on the board here, but he does mention that in the textbook. We're more interested in how the mean fluid temperature varies with X, the two boxed equations over there. So you got to be a little bit careful here. If you have a fluid in here, and what happens as it goes on the tube, it keeps getting hotter and hotter until something bad may happen. You might have vaporization of the fluid in there. You may have an explosion of steam or fluid in there. This could be danger because it keeps getting hotter either until the tube ends or something bad happens. Down here, no, don't worry about it too much because it's never going to get hotter than the tube surface temperature. It's exponential. It approaches asymptotically. So, yeah, there's different characteristics of what happens in these two situations. Okay, now, here we go again, chapter 8. What's the whole point? We got to find H. H is the key. So that, again, is our big goal. Chapter 6 and 7, it was the same thing. Find H. Chapter 8's the same thing. Find H, which we're going to do. But before we do that, let me, I didn't mention, but I want to mention over there, how do you find X fully developed? So let's see if we can get the equation there. Here's my equation. I'm going to put that, I think, right here. Okay, let's put that right here. To find X fully developed. Okay, let's, and again, Reynolds number for the diameter is less than 2,300. Laminar, Reynolds number greater than 2,300. Turbulent, and X, this is for laminar flow. Okay. X fully developed divided by diameter. The ID of the tube is approximately 0.05. Reynolds number D. And for the thermal boundary layer, there's two fully developed regions. One's for velocity, that's the guy up here, and there's one for temperature, that's the guy down here. They can be different. For turbulent flow, X fully developed over D is much easier. X fully developed temperature over D, much easier because turbulent flow is so mixed up that there's no Reynolds number in there, there's no Prandtl number in there. The textbook says we're going to use the magic number 10 for both. So, same equation for both because of the nature of turbulent flow. Okay, so let's play a little game here. Let's say laminar flow. Let's get X fully developed. .05, Reynolds number D times the diameter. 0.05 times 1,000. D is 50 diameters. If diameter is 1 inch, X fully developed is equal to 50 inches, about 4 feet. So there it is, a 1 inch tube. The Reynolds number of the tube is 1,000. How long does it take before the velocity boundary layers get to the center line and combine for the fully developed region? About 4 feet. About 4 feet. Okay. Let's do the temperature one. X fully developed temperature. Let's take water. So I took water, Prandtl's 6 about. So X fully developed for water is 6 times 50 is 300 D. If D equal 1 inch, X fully developed temperature is equal to 300 inches, which is about 25 feet. So water in a 1 inch tube, laminar flow at 1,000, it would take 25 feet of a 1 inch tube before the boundary layers developed to meet at the center line. And then let's do air. For air, Prandtl, I took about, I think, 0.7, yeah. There should be a temperature here too. Oh yeah, for air, it's not 25 feet like water, it's 3 feet. Why are these guys important? Oh, because things depend on how rapidly the flow develops in the tube. The heat transfer, obviously. where do you think the biggest heat transfer in the tube is right now in there? Well, on a flat plate, I'll tell you, where was the most heat transfer on a flat plate? Right at the front where x equals 0. Big heat transfer here. As the boundary layer gets thicker and thicker, the heat transfer goes down because the boundary layer serves as an insulating blanket of sorts. So yeah, we engineers need to know that. In your automotive radiator, you've got vertical tubes carrying water. I guarantee you, it's critically important to know if that flow in those radiator tubes is in the entrance region, totally, or maybe it quickly develops where most of the tube is in the fully developed region. Oh, that's critical for the designers of the radiator and heat exchangers in general to know what's going on there. There's two things going on here. Here and here, velocity, temperature. Assume Reynolds number is turbulent. X fully developed equal 10 times diameter. X fully developed temperature, 10 times diameter. If it's a 1-inch tube, both those fully developed distances are 10 inches, less than a foot, less than a foot. At what Reynolds number? I don't care. There's no Reynolds number in the equation. Here's the equation right here. Do you see a Reynolds number? No. But of course, the Reynolds number has to be greater than 2,300. That's the limiting one we have. For any Reynolds number greater than 2,300, there they are. Very, very simple. The textbook, by the way, says that this guy can vary between 10 and 60. And he says, but we're going to use 10 as the magic number. So the textbook said use 10. We're going to use 10 in our example problems and homework and so on. Okay, so yeah, it's critical for the engineer to know about the flow pattern and if the flow is fully developed or not. All right, this is a good introduction stopping point, so we'll stop for today. If you came in late, look at the board on the right for our changes in homework and exam dates, and so then we'll see you on Wednesday.